Okay, all right. So last time we were discussing transformers, and we defined and wrote down an equation for a transformer that involves the primary voltage, secondary voltage, and the number of turns on the primary coil and number of turns on the secondary coil. We derived this by using the conceptual understanding of a transformer, right? So, any questions from the last lecture?
No, sir.
Okay, no questions. All right. Okay, so I will take this same diagram that I drew, this one, and let's talk about the transmission of electrical energy in these wires, right? So let's take this diagram onto the next page. Okay. So what was this diagram? Basically, from your electrical supply or company, you get some voltage. You send your voltage at a very high value for voltage through these long wires that are these cables that are held on these poles. These are called transmission lines. It's because they transmit electrical energy, which is in terms of this potential V. Now, this happens, and then we have a transformer which steps down that voltage V, 10 kilovolts, to a 230 volts. In some countries it's 230, in some countries it's 220. It depends, right? Now, this 230 volts, can you tell me which voltage is this though? Is it the peak voltage, or is it the r.m.s, root mean square voltage?
Is it the root mean
Anyone?
square?
Sorry, can you repeat?
Is it the root mean square?
It is the root mean square velocity, as not velocity, sorry, the root mean square value for voltage. Again, it is the voltage that you would be usually getting out of this transformer. This is also the mains supply voltage, right? Now, obviously, the peak voltage would be higher. I think it comes out to be 255 or something. We calculated it, right? You just multiply it with √2, and that voltage is the peak maximum voltage. But because you have an alternating current, right? So you will always get an average value of the voltage instead of getting peak or minimum values of voltages. You always use the average value, which is the root mean square value. So this is the r.m.s value of the voltage. Okay, now let's see. Suppose that this distance is very big, right? Suppose it's 100 miles or about 200 kilometers or something. So we want to transmit this electrical energy through this very long distance from the main electrical supply that's coming from the power grid, and send it to our homes, right? Homes, offices, or whatever, right? To the buildings. That is done using these cables. Now, the question is, why do I need such high voltage to transmit, or why do I need such high transmission voltages? Can you take a guess? Why would that be?
Because of the resistance of the wires?
Because of the resistance of the wires, right? Exactly, right? These wires, they will have some resistance let's call that, let's say that this is the same wire, right? And it is like this. So they both will have some resistance. Let's, for the sake of argument, let's say it's 10 ohms, right? So the resistance of the wire is 10 ohms. This will cause a significant drop in power, right? There will be lots and lots of power losses in these cables, right? Now, let's see why when we take such high value of voltages and transmit that, which is 10 kilovolts, that is more beneficial, and we get much less power loss in terms of if I were to just transmit 230 voltage and get rid of the transformer altogether. We'll just now see why that cannot work, and we do need a transformer, because the power, I can compute the power coming from this main grid, right? The main grid, if it's sending any voltage, suppose it's sending 10 kilovolts, right? I can compute the power by multiplying V and I. Now, suppose that there is some current running through these wires, and that is I equals to 4 amperes. Now, this current that runs through the wires depends on the potential difference, right? So suppose if I have some value of potential difference, the value for the current will be something else. If I have another value of potential difference, the value would be something else. Okay, let's see if I did not need a transformer, and I would send V is equal to, suppose I'm sending V is equal to 230 volts, and I don't use the transformer. I don't use it. I just send a 230 volts transmission supply. So the power that would be produced from that is 230 volts times 4 amps, right? Actually, let's make it, let's, for the sake of argument, let's make it 250, right? Just to make the mathematics a bit simpler. Now, if it's 250 times 4, then this would just be 1000 watts. So you're getting a total of 1000 watts. Now, suppose, so this is when I'm using a voltage of 230 volts and transmitting that. So this is the transmission voltage, right? So this is VT, transmission voltage. Suppose now if I use a transmission voltage V of another value, this 10 kilovolts, which is 10,000 volts. Using this value and transmitting this amount of voltage will produce a power of what? Let's see. For V, so it would be VI, and for V you would have 10,000. But remember, because of this relation V is equal to IR, V and I are directly proportional. So how much did I increase to go from 250 volts to 10,000 volts? I'll have to divide the current by that amount, right? So can you tell me how much of an increment is from 250 to 10,000?
2500.
250. No, it's 40, right? 2500.
Oh, you're asking for the current hour.
No. I'm just asking that how much of an increment is there in this? So as in, how much do you multiply 250 to get 10,000, right? So because V and I are directly proportional, so the number that I'm multiplying or scaling my potential, the current has to scale down. If I'm scaling the potential up, then the current has to scale down, because again, this is R is equal to V by I. And R is a constant throughout this resistor wire. So if I'm scaling the potential up, the current scales downwards. How much will it scale down? Because they're directly proportional to each other, it will scale down by exactly the same amount by which I scaled up the potential. Does that make sense?
Yes.
Okay. So this would be 10,000 volts. And what would be the current then? I have to scale it down by 40. So it would be 0.1 amperes. Okay. So this is now 0.1 amperes. What does this give you? You'll see that this gives you 1,000 watts as well. Okay. So you might say that we're getting the same input power or the power from the grid. So where's the difference, right? Now we'll see that the difference is when we talk about power loss. That is when we include the resistance of the wires. And you know that a power loss in any resistance is given by I squared R. Now this equation will determine the power that is lost in these wires. So what would that be? Suppose if I'll do it for VT is equal to V to 30 volts. If I have this thing, then what would be the power loss? It would be, because R is 10 ohms, so P is equal to, corresponding to 230 volts, I had 4 amperes. So it's 4 squared into 10 ohms. This is 16 into 10, which is 160 watts. So you can see that there is a power loss of 160 watts in the cable, right? And this might seem quite less, because we're getting 1,000 watt. We're sending 1,000 watts of power, and if there is only 160 of it is lost, then what's the big deal? But again, we chose the resistance of the wire to be 10 ohms, which is not a very big value for resistance. Usually it is a bit, it is a lot higher, and you'll get a very big power losses. But we want to just see the comparison. So now let's compare it with the power loss for VT is equal to V 10 kilovolts. Now for this thing, if I compute power loss, I get, now the current has scaled down for this voltage, and that scale was, it scaled down to a value of 0.1. So 0.1 squared, if I square 0.1, I get even smaller number. Now that multiplied by 10 ohms will be what? 0.1 watts. So do you see the difference? What does this tell me? Can anyone volunteer and give an answer? What does this tell me? The comparison of these two values.
Increasing the voltage decreases the power.
Yes. So it in more accurate words, a higher voltage transmission voltage is going to reduce the power loss in the cables by a very significant amount, right? So how much power loss has been reduced over here? Can someone tell me that? So I can just check. Let's see how much power loss was I able to reduce. How do you do that? You just take the ratio of the two numbers, right? So 160 divided by 0.1. Both are in watts. What does this give me? Can someone do the math? 160 divided by 0.1. 0.1 is 1 by 10, so it would go upstairs, and this would be 1600. This is the number of times that I was able to reduce the power loss. I reduced 1600 times of the power by increasing the potential to 10,000 watts. So you can see that we were able to reduce the power loss by a very big significant amount in the cables by just using a very high potential or transmission potential, right? What does this tell you? This tells you that the smaller the current, the less energy is wasted in the cable. Right. Does that make sense? Is that clear?
Yes, sir.
Okay. All right. Okay, now a small question. Why do I require AC current to transmit electrical energy or electricity? I mean, you could have, why not? Why didn't we use direct current instead? Why do I need an alternating supply of current for transmitting electrical energy? Any guess? Again, think in terms of the energy losses. Okay, so because AC current means that we have alternating voltages. Alternating voltages means we have alternating energies, and these type of voltages, as we saw, are very easy to step up and step down. To step up and step down. Again, because when we have this AC supply, we saw that we can use the concept of a transformer, a primary coil and a secondary coil, and then apply the laws of electromagnetism, which was that the alternating current is only capable of producing an alternating magnetic flux in the primary coil, in the coil, right? Not the coil, but between these two, there would be a material connected that connects kind of these two coils, right? I forgot to mention this. It's usually an iron core, or sometimes it's called iron former. Right. So only alternating current is capable of producing alternating magnetic flux in this iron, right? Now, this alternating magnetic flux that was transmitted, it is cut by the secondary coil, and then we saw that that is what is responsible for the changing magnetic flux, and then that gives rise to the alternating EMF produced across the ends of the secondary coil. Which means that alternating voltages can be stepped up and stepped down. What does that tell you about the energy? This means that the energy losses in AC would be significantly less than DC, because DC we have a constant supply. So this is DC, right? Suppose, let me draw it like this. This is time, this is current, or let's say it's voltage. There's a constant supply of voltage at one particular value of voltage, and that voltage is the same throughout the entire time, right? So you're just supplying, there's just a constant supply of voltage throughout its course. But an alternating voltage would look something like this. Now, what's the difference between the two? In an alternating supply, the value of voltage starts from some value, in this case 0, increases, but then decreases. And if the voltage is decreasing, energy used or energy loss will be minimized, right? Energy loss will be minimized, and then again it goes down and down and down, so energy loss is being minimized, and then it goes back again up, so there is some energy loss. But because we don't have a constant supply of voltage throughout its journey, the energy losses are minimized. Does that make sense?
Yes.
Is it clear?
Sir,
Okay.
can you repeat this part again?
Okay, this one, that what's the difference between AC and DC in terms of energy loss, right?
Yeah.
Yeah. So again, in DC direct current, you have a constant voltage supply. It's not alternating. It's not changing. So there is a constant supply of voltage. Suppose it was 10 volts. Suppose, for the sake of an argument, it's 10 volts. It will be constant throughout its entire time. There is no decrease in voltage. And we know that voltage is directly related to power or power losses or energy loss per unit time. Now, if the voltage is at the same value of 10 volts throughout its journey, compare that with a voltage whose peak is still 10 volts, but this is 0, and it starts from here, it increases, but then it decreases. So the voltage starts to decrease. It's not constantly 10 throughout. First it's 0, 1, 2, 3, 4, 5. So at this instant, maybe it's 1. At this instance, maybe it's 5. At this instance, it's 10. And then again, it starts to decrease. Maybe it's 7. And then, right, you get the point, right? So these are the values of voltages. And there is, throughout its journey, there is not a constant voltage of maximum peak voltage. It's not like that. At some points, we have less voltage. At some points, we have peak voltages. But at the other points, we have less than the peak voltages, 5, 7, for example, right? So when I compute the power loss, an average power loss for this alternating supply, because the voltages are alternating throughout its time, it will reduce the amount of energy that is lost compared to this one, 10 volts, where I'll constantly be getting energy loss coming from 10 volts at every point in time. So when I would compute the energy loss, I'd be just putting a constant value of 10 throughout my calculations, while in this case, I would, at some instant of time, I would have some value. At another instant of time, I would have some other value. These values would be less or equal to the peak voltages, which is 10 volts in this case, right? So that's why the energy loss will be reduced significantly compared to direct current or direct voltages. Right. Is that clear?
Yes, thank you.
Okay, let's do a problem. Let's start with a simple one. Suppose that you have an electric car or electric train or a car, and it operates at V is equal to 12 volts of an AC supply, A dot C. Let's calculate the turns ratio for a transformer that would be suitable to step down a mains voltage of 230 volts. Again, you have an electric car or the one it works by using 12 volts of AC supply is required to get it running, and in your sockets you're getting 230 volts of supply. You want to reduce the supply that is coming from the mains by using a transformer in the brick or the plug that you're using to connect the electric car. So we want to calculate the ratio of number of turns for these this transformer or this coil to step down the voltage from 230 to 12 volts. So is the statement clear?
Yes.
Okay, so how would I compute this ratio? What I want is the ratio of number of turns, because again you have to remember why ratio just means that we have two coils that make a transformer. One is the primary coil and one is the secondary coil. So how do I calculate this ratio of number of turns that are required? We'll use the transformer equation, which was that the ratio of EMF induced in secondary to primary is equal to the ratio of number of turns to secondary to number of turns of primary. Right? Now, although I cannot compute the number of turns, I can definitely compute the ratio. So the ratio can be computed. The ratio that I require is NS over NP. And this ratio will be equal to Vs over Vp. Now, the thing that you have to figure out here is what voltage is Vs and which voltage is Vp. Can you tell me?
VP is 230 volts and VS is 12.
Exactly, right? So Vp, which is on the primary coil, and we know that on the primary coil is the voltages that we are sending, so that we want to step up or step down, right? So we want to step down to 30 volts to a value of 12 volts. So secondary will be having 12 voltage, which means that if I put this back here, I get 12 over 230. This math gives me a ratio of 1 over 19. What does that mean? Can you tell me? So I computed this ratio. What does this ratio mean?
If the primary coil has 19
this.
turns, then it means that
Yeah,
the secondary one would have 1.
Yeah. So if you rearrange this as ns equals 1 over 19 times np, or as 19 ns is equal to np, you can immediately see that this means for one number of turns on primary coil, you would require 19 number of turns, right? So any questions?
No, sir. It's clear.
Okay. So let's do another one. Okay, suppose you have a heater, an electric heater, and suppose that it's rated at 12 volts and 16 or 96 watts. So it's 12 volts and 96 watts, and it's run from a transformer which is connected to a mains supply of 230 volts. Okay, so now assume that there is no energy loss. What does that mean? That means that the power that I'm giving in the primary coil should be exactly the same as the power I'm getting at the secondary coil. There should be no loss in power, right? So this statement is what gives you an equation to solve this problem. First of all, let's compute the current in the heater, right? So how can I compute the current? I have P and V, right? And I know that this P and V that are given to me are secondary values, VPS and VS. So this is P for secondary, or let's just say it's P, which is equal to VS IS. And this gives you IS as P over VS, which is 96 over 12, which is 8.0 amps. So that was the current that flows through this electric heater. Now, I want you to compute the current input to the transformer. The current input to transformer.